All right, let's get started. My name is Alex Turner, program manager on the Managed Languages team at Microsoft. We do the Visual Basic and the C# compilers. And what I worked on really primarily for the last release was the C# and VB support for async, the await keyword, if you've used that. I guess how many people here have used await, have tried it out in VB or C#? Okay, good, most of you. This talk is really about the things we've learned having had async out there for now about 8 months and seeing what kind of roadblocks people run into, what kind of tips would really help unblock people as they're trying to explore and use async. Some of the other program managers in our team, especially Lucian Wishick, he's gone out into the forums and he's seen the questions that people are asking about how do I use async void methods, when does that make sense, things like that. And so what we wanted to do is kind of come here and bring those core set of tips, distill it down really to 3 categories of tips, and help you get past those kind of initial learning issues around how do I use async in the right way, because there's a lot of places where it really kind of cleans up your methods, and there's some little pitfalls you can fall into that are worth knowing about. You're probably going to get the most out of this talk if you've already seen something about async before or you've played with it yourself so you have the basic idea, but we're going to go through a quick overview at the beginning. And so kind of just to set the stage, the 3 core tips that I'm going to be giving today are really that async void, you want to think of using async void methods for top-level event handlers or for other constructs that are sort of morally equivalent to a top-level event handler. You can also make tasks that wrap existing events, and we're going to see some places where you have sort of the event-based world and the task-based world meeting, and some ways you can bridge that gap. And we're also going to talk about how you can use the thread pool when you have CPU-bound code, right? Like async is great for when you're on the UI thread, or you're on a very single thread that you want to operate on, and you want to dispatch events and free up your UI thread. But sometimes you actually just have CPU work that you want to do, and it's important to know how to actually go off to a background thread and pull that back in and do that in the right way. So sort of core to understanding async and really the underpinnings of most of the tips here is really getting a sense for how that flow works, for what exactly happens when I'm calling into async methods. You probably have written code like this if you've tried out async. You have methods like event handlers that have awaits in them, and maybe some async task methods, some helper methods that you've written that also have awaits. But what exactly is happening under the covers as you're going through that control flow? So sort of the core of this, when you're in something like XAML, WPF, WinForms, really any of the UI frameworks we have will have a message pump underneath them. And that takes care of taking the queued messages and processing them one at a time. Things like mouse moves, clicks, that's make hovers work, all the animations you have in your UI. And so for example, let's say the user clicks. A click happens, control flows into our button one click event. And then the first line, the button one click, is saying await load settings async. And so we saw, well, we have to evaluate the expression load settings async, and that's a task returning method, so we have to get that task. We go into that method and we call it, and you see control flowed into there. Then io.network.download async, right? That just represents some sort of asynchronous API that I'm calling that I want to get a result from. And I call that, and I get back a task object. That's that core object, that future object that async APIs are powered by. It tells you in the future, hey, some value is going to be available. I'm going to be able to notify you when that's ready. And we get back that object, and we can hold on to it. That's how we track when the download is going to be done. And so we take that object, and we immediately hand it over to the await expression. And so we're telling the compiler we want to await this. We want to pause our execution inside load settings async, and we want to come back when that download is complete. And so we await here, but the key to how await works and the way that it's able to actually make your method pause is the first time you get to an await, your method returns. Your method returns that task that we've promised, the one that's going to notify people when we complete, when load settings async is done. We're going to return that to our caller. And so you see the next thing that happens is we return a task, in this case the load settings async task that the compiler created for us. We return that task back to button one click. And so we now have that there. We're immediately taking that task. We're awaiting it. And so we await it, and that makes button one click return. And button one click was called by the message pump. Whatever UI stack we are called us. We're going back there. And now we're back in the message pump. We can process other messages. And so we've kicked off the download. We've called into 2 methods that have kicked things off, but we've immediately returned all the way back where we started. And that's what keeps the UI flowing. So now we go back around the message pump. We can handle other clicks, right, because the UI is responsive. But now let's say the download completes, right? So the download finishes, could be 1 second, 10 seconds later. The download finishes, and that means that we now resume back where we left off inside load settings async. So I'm just going to go back again. So that was the key. So inside load settings async, we awaited that download task. And what that did was it signed up the rest of the load settings async method as the callback, as the onCompleted callback, basically. And so we say, all right, well, now that the download's completed, it has a hook of that callback. It's going to jump back into the method where we left off, and we're going to pick up execution. And so now we're able to return. We get to the end of our method, we return back, and we're now off the message, or we're now off of our thread. We've returned to the message pump again. And so what that means, though, is that we have completed. Load settings async has completed, and so we signal that we're done, right? We signal that our task has actually finished now, and that gets now scheduled as a new message on the message pump. So load settings is now waiting to go trigger its completion. And so we travel around the message pump again. We get to that message, which puts control back here in our parent method. And so our parent method then continues, does update view, and we flow back around the message pump. And so that ability for us to quickly return back and then come back in only when things are completed, that's the core way that async and the await keyword work, and the way that they actually let you make these pausable, resumable methods. And so that was kind of a quick tour of exactly what happens under the covers. But you saw that we had two different kinds of methods there. Actually, if you go back, there was the async void method we had, and then ultimately there was the async task method that we wrote, that helper method that we had. Well, when do you write async void methods, and when do you write async task methods? That's one of the more common questions that we get, and we think it's actually probably the top point of confusion that we want to help address with async. And so we'll get complaints like this. People will talk about this on the forum. We'll say, well, I have this app. I wrote it. It uses async, and it mostly works, but not 100% of the time. It seems like there's some sort of condition where, depending on how fast or slow the network is, something's going on. It seems like it doesn't actually go control flow where I expect it to all the time. And so at this point, when we hear that kind of complaint, a good sort of first warning bell is, well, is there somewhere, perhaps deep into your code, where you're using async void that you actually meant to use async task? And so one example we have of that, we had a customer app that was written in Silverlight using the async targeting pack, so they could use async. And the customer had this quote here saying, well, I have a Silverlight page that uses RIA services async to load data for the page. It works fine if the user waits for a few seconds before they go to select the print button. But it doesn't work if they click print right away. If they click print before all the data is there, the printed output doesn't seem to have all of the data. So the data's there, but it's not kind of fully queued up yet, and the user hit print. Like, what's kind of going on here? Why do I have partial data, even though it looks like I should have everything? And it kind of makes us think, well, is there something going on there? Are you potentially not actually waiting for that to finish? Are you using async void methods and hoping for the best, right? Are you guessing when things are going to be done? And so this is a good thing you want to go dig into. So kind of, if there's one key takeaway that you have today, just one, so for goodness sake, stop using async void everywhere. This is really probably the largest issue we've seen, right? And in terms of customer apps that have issues around async where it's not behaving as they expected. You want to think very carefully before you use async void anywhere that isn't a direct event handler, or you overriding some sort of on-click, on-completed kind of event that's coming that's sort of a moral equivalent of an event. And so, we don't want to go into that specific app because the code was kind of involved, but I'll show another simpler example, and this is something that actually bit somebody at Microsoft when they were writing one of the Win8 samples early on for the Windows runtime. And you see the code here. There's button one click. That is our async void event handler. And the first thing it's doing is it's calling this send data method. And send data, as it should, is using await to stay responsive when it's calling get response async. I want to go out to the web and get that. I want to come back, and then I'm going to process it. So that's good. We're keeping asynchronous there when we're doing network access. But what we care about is really waiting until that data is back, right? But the code we have here isn't exactly doing that. And so if we watch the control flow here, we're coming in. We're going to send data. We're going to kick off that request. Remember, send data is going to go in. We're going to flow until we get to that first await point, right? We're going to set up the web request. We're going to kick it off, and then we're going to return because we want to return control back to the UI thread. But unfortunately, we don't actually have any way for button one click to know when this send data method actually finishes. We didn't give them back a task that they could use to track when the helper method finishes. We just returned void. And so it's going to go back, and then we're just going to get off back onto the message pump. And now we have now is a race condition, right? Because down there in send data, well, maybe that one's going to finish first. Maybe the download finishes first. We continue, we process it, and we set that get response, that sort of member field on our type. And if we do, then when we go to print it above, we'll be fine. But let's say that 2-second delay that they put into button one click, let's say that finishes first. Maybe the network is being really slow. It takes 5 seconds to finish the download. In that case, after 2 seconds, get response is still going to be blank. The download didn't actually finish. And we're going to go on and we're going to print that out. And you can sort of imagine how this sample came to be that way, right? Like somebody wrote the code originally without the delay. It seemed like the variable was never filled in. And so, OK, well, maybe I'll have a delay for 500 milliseconds. Maybe that'll do it. And then it seems like it's still not responsive enough. Maybe 1,000 milliseconds. And it seemed like 2,000 was some sort of good balance, right? But then you put it out in the world, and you might have delays longer than 2,000. So that's not the best way to synchronize and wait for data to be ready. And so we'll take a look at what we could do. Let's actually see one more problem with having this set up here where we're using an async void method. What if something goes wrong when we call the download? Let's say we have get response async and there is an exception, right? Out there in button one click, there was a try catch. So there was an attempt to say, all right, we're going to have a try catch block to actually catch an exception to say if something went wrong, we're going to notify the user. But look what happens if there is an exception. We come in to send data. We go down and we go to request.getResponseAsync. We kick it off. We get to the await. And we go return back. But when we return back, we're already done. Like we just kicked off the response, but we didn't wait for it to finish yet. We immediately return. We flow out. There was no exception. We exit the catch block. We leave the button one click handler. Now we're done with it for good. Eventually, we get the response back, and we continue. Oh, now there's an exception. The await throws the exception, and it has nowhere to go. The await or the callback is now sitting directly on top of the message pump, which scheduled that continuation. And the exception just goes and it blows up inside the message pump. And depending on what UI stack you have, it might go to like an unhandled exception handler, or it might just kill the app. And so you really need, not just for knowing when something completes so you can move on, you also need the ability to know, well, if it failed with an exception, I want that exception to bubble out to me at the call site. And that's another reason why you really don't want to use async void there. You want a task that can actually capture that exception. And so async void, what you really want to think about there is having async void being a fire and forget mechanism. You use async void in contexts where you don't care to know anything about what further happens. If async void methods that you call could have exceptions, you really need to have them have their own try-catch block that would catch any exception that might possibly happen. And the thrust of that is that the caller can't know when an async void method finishes. They can't catch exceptions from them. They're going to just get thrown back to the UI message pump. And so, you want to use async void methods when you have those click events, when you have those top-level things that the caller, the message pump, doesn't care about, right? The message pump doesn't really care when logically your flow for clicking has completed, right? But you care when your flow for downloading has completed. And so typically, in the 99% case, for the methods that you write that are helper methods using async, you're not going to want async void. You want to use async task for those cases. And so what you really want to do here is remove the void, make it task, probably rename the method to send data async also, and then make sure that you're awaiting it up there in button one click. And that's the key. And just because you're using task, it doesn't mean that you have to have a return value come out of the await, right? Like you've seen us use task of int and task of string and things like that, and when you await that, you get out the int or you get out the string, right? But even if you have no return value, no logical return value, even if you just want to only know when something completed or failed with an exception, you can just use the non-generic task by itself. And that's a task where when you await it, you get back void. The act of awaiting that task gives you void, but you still get to know when did it finish. You still get to know if it has an exception that'll be rethrown, you can catch it in your outer block there. And so the alternative is not between async void and then task of t. It's really between task and task of t. And you want to use async void sparingly. And so in this case, we could do this transformation you see here if we want to kind of keep that flow where we put something into get response and get it back. Probably actually what we want to do is change send data, in this case, so it does return task of string, because we have a logical return value. We actually are attempting to get back some sort of response, and we want to return it. So another case that we've seen is people saying, well, I'm initializing something, especially in my async void load state method. Async void load state has seemed to be, since Win8, a big issue that we've seen in the forums, where, well, I'm setting stuff up in load state, but it seems like kind of half the time it works and half the time it doesn't. Like in this case, I'm checking my pixel width, but sometimes it's 0. Why is it 0 inside onNavigated2? And so, we trace it through, right? You want to see what happens. Like, we don't, as the C# team, we were less familiar with these templates. We wanted to go and take a look and see what happened. And we see onNavigated2. Well, onNavigated2, somebody made that async void. That's actually fine. OnNavigated2, it's not an event handler, but it is sort of logically an event handler. There's a navigated2 event, in essence, on the base type, and you give it an overridable method that you can go implement that lets you specify what you want to happen there. And so this is a fine use of async void. But when we see what happens there, we call base.onNavigated2. And when we go to base.onNavigated2, we look through, OK, it does a bunch of initialization, and then it calls, later on, after it does some stuff, that load state method. And load state is another one of these overridable methods. And that's one of those things that we implemented there below. And so the flow is, when our page is navigated to, we're going to come into the onNavigated2 method. It's going to go back to its base implementation, which we see calls back into load state, and then we're going to get down to that first await. But we get down to the first await, and then we immediately return, and we return control all the way back to the XAML message pump. And so what do we have here? Well, we have the same kind of race condition again, right? Which of those two awaits is actually going to finish first? We're playing an intro sound in onNavigated2, and we're getting a file from local storage, right? And depending on the length of the sound and the speed of the disk and how much other stuff's going on, either one of those might finish first. And what we're hoping happens is that the file is gotten, we do set source async below, and then that's going to go up to the top, and then the image will be all loaded, and we're good to go. But if the sound downloads first, we continue going in that onNavigated2 method. There's nothing there yet, right? And so we want to be able to fix this race condition. We don't want to be hoping that one thing loads before another. So here's an alternate way that you can think about it, and it uses the fact that these task objects you get back from async methods, including the async methods you write, are first-class objects. They're objects you can hold on to, you can store, you can get them in one method, put them somewhere, and await them in another method. And that's what we're doing here. And so, inside load state now, rather than doing the loading directly, we made ourselves an async helper method that's going to do that loading for us. It's going to say, all right, make the bitmap image, do all the stuff, and return it. And we take the task that's associated with doing that loading, and we store that task, right? And so now, we know that we're at least going to get that far to where we're going to store the task, and when we get into onNavigated2, when we get to await, we're now awaiting for that stored task, right? And so this is the way we kind of set up some state in load state, but we're awaiting it now inside onNavigated2. And we know that we're synchronously going to get to that loading, right? And so this is where you can kind of thread through a task back to some other place where you know you're going to want to care when something is done, and then await it there, right? And you can think of all different kinds of uses you can use for moving tasks around in this way. You can add tasks to some sort of queue. You could have some sort of work stealing thing where you add a bunch of tasks and then you're starting to pull them out because oh, okay, I want to show 5 items at once, and when one is done, I want to show another one, and I'll pull the task out and start examining it. You can do those kind of operations on these first-class task objects because you can store them and load them back later. So, there's a few examples I showed. There's actually some more. If you get the slides afterwards, you can look through. There's some hidden slides that go over a few more cases around things like async void, including what you do in constructors, right? You're not allowed to wait in a constructor because that is sort of like a synchronous place where people expect something to come back with a synchronous result value. So what do you do there? We tend to see people using factory methods, sort of async factory methods when you sort of have an async construction need. You can't use async in property getters. It's the same kind of thing. You expect it to return synchronously. So people will make sort of get foo async methods in those cases. And when you have async event handlers, you sort of get new, interesting issues to deal with. Like what I like to say there is sort of with great responsiveness comes great responsibility. That you have these new problems that are actually good problems to have, right? I have a responsive UI. It's not hung when I'm doing an operation. And so now, well, what do I have to do? Now I might have to care about cancellation. I might have to care about progress. And one of the things is you might want to care about reentrancy if people can start clicking on those buttons again. So the trick there is to go disable the UI in the interim. And so we have some more code that you can explore in the slides afterwards. So one other thing I wanted to point out, though, really around async specifically, is async lambdas. And what we let you do, and if you have a place where you want to put a lambda, you want to send a lambda to somebody, and you happen to need to await inside that lambda, we let you put the async keyword, not just before methods. You can also put async before lambda expressions. But when you do that, you have to be very careful. And there's a pitfall you can fall here about whether your async lambda is void returning or whether it's task returning. And so both of the lines above are actually valid, right? You see that they have the same body, but one is assigned to something of type action, and one is assigned to something of type func of task, right? And so action is a delegate that returns void, and func of task is a delegate that returns task, right? So the top one's going to be void returning, and the next one's going to be task returning. And you're able to do both, so you can talk to existing APIs. So the question here is, I'm calling task.run to put some code onto a background thread. I want to go do that. Well, which overload of task.run is it going to pick, right? Because inside, I'm awaiting. So it better pick one that's task returning. Otherwise, it's going to say that it's complete while the method it called is still going, because it has no way then to track when my lambda finishes, if my lambda was void returning. Well, luckily, we do have both overloads on task.run, and in C#, we will prefer the func of task overload if we see one. So we're going to call that one rather than the action-based one. So we're good to go there. And so that works out. If you're coding in Visual Basic, you have sort of a similar issue, but you have a different way of addressing it. In Visual Basic, the method that we call, the overload that we call, is going to be directly based on the signature of the lambda that you generate. And you actually make that call directly. So if you say async sub, the lambda you get back is a void returning lambda. If you say async function, the lambda you get back is a task returning lambda here. And so it's based on the structure that you put into the method itself, into the lambda itself. And so if you have something like async await task.run and you're going to pass it a lambda, you have the choice. You could send async sub, you could send async function. And so you want to remember to write async function in those cases. And this is a case where if they're both there, the compiler will actually warn you that it thinks you're probably doing the wrong thing if you write async sub by accident. So one other thing is when you have dispatcher.run inside, this case specifically inside the Windows runtime for the XAML support, you're probably used to using dispatcher.invoke, dispatcher.run to actually schedule work from a background thread back into the UI thread. And so that work that you want to schedule, especially if it's going to do UI things, it may want to be asynchronous so that you can await. But you have to watch out here. This is one of those cases where sort of when you're writing this code, you want your little warning bell to go off to make sure you're doing it right. You're calling dispatcher.run. You're passing this async lambda. Well, is this going to be an async sub lambda or an async function lambda, right? Am I going to return void or am I going to return task? Well, if I want to go, I could look at the signature for run async. You hit F12 and do go to definition. You could see, all right, well, it takes a core dispatcher priority, and it takes a dispatched handler. That's a delegate type. So you hit F12 again, you go into dispatched handler, and you say, well, what is a dispatched handler? That is a delegate that returns void. And so it returns void, which means that when we send that lambda expression in, it's going to become a void returning lambda, right? And so what that means is we're going to have an issue here with our control flow. I'm going to come in, I'm going to say, all right, well, we're calling this method. We're going to get to the first await. But when we get to the first await, we're going to immediately return back to this await and then continue going. And so if there's this exception later that comes back from throw new exception, it's not going to be caught, right? Because we didn't return task. There's no way for this outer code to actually know about that exception and catch it. So one of the things that's actually in the slides, if you check later, there is an implementation for how you would call dispatcher.runAsync, sort of an extra overload you can define yourself, a helper method you can define that lets you take a func of task, and it's going to do that kind of transform for you so that exceptions behave as you'd expect. So that is that key. Remember, async void is for fire and forget. It's for top-level things only. You don't want to use async void elsewhere. You don't want to start putting it for your helper methods because you probably do care about when those things complete, and you probably do care when they fail with exceptions. And the one extra bit of thing to watch out for there is for async lambdas. You want to make sure that you're using async task lambdas in all of those cases, unless you're subscribing it to be an event handler, like for a click event or something, right? It's the same kind of guidance. If you're doing something where you really probably do care about exceptions in your outer code, make sure you're actually dealing with an async task lambda there. So we also have this idea of sort of event-based programming, right? This has been around for a while. It's actually very useful in UIs, right? I have a click event. I have a mouse move. I have this button was, double-clicked and it was dragged over here. We have all of these useful events. And these events are actually useful because typically they're handled and you care about them in isolation. For a lot of the code you write, When someone presses the button, I do some action and I return. And when they set this option, I do some action and I return. And there's not a lot of complex state that I have to track sort of across all of those different button clicks. But a lot of times, it turns out there is, right? Like, depending on exactly how complex your UI is or how sort of fancy you want animations to be and when you want things to be set up, you may actually have a lot of interrelated controls that need to care about a lot of different state. And if you're doing that, there's a lot of pitfalls you can fall into where your code quickly kind of becomes spaghetti code. And so we'll go back to that same app that we saw there. And I have another customer quote that I want to read here. Well, you think of, all right, we have this Silverlight page. The user's clicking print. We weren't seeing all the data. Well, we got rid of our async void methods and our task.delay, but can I use await in some way to wait for the onCompleted event? Is there some way that I'm using RIA services async, it has an onCompleted event to tell me when something is available? Can I await that so I don't have to kind of guess, I don't have to watch the data and have delays? Can I just say, when it's completed, do this, without my code turning into spaghetti? People often will describe, spaghetti code, and they'll be talking about their code getting all bundled with like nested lambdas and such. My favorite term, I talked about this in one of my previous talks, my favorite term for that is actually macaroni code. When you have a lot of these nested lambdas, these tiny nuggets of functionality that are all kind of bouncing between one another in lieu of actual simple linear control flow. And so, forms over data apps and these business apps are necessary and critical, but they don't make as exciting demos. And so I'm actually going to show the same kind of problem happening with another complex UI, which we had from a customer who talked to us about this app. They were making a Windows 8 app, a Windows Phone app. And the idea here was you want to make an app for kids. You want kids to be able to kind of drag things around on the screen and learn how to count. So the idea is you have a tree and you have a bunch of apples in the tree. And as the kids are dragging the apples from the tree into the basket, they can be counting those apples and figuring out how many there are, and then move on to other levels and so on, right? And so, the guy created this cool UI here, and the apples will actually kind of wiggle and wobble. I'm actually going to show you here. I have a copy of the app. And so I go into here. And so the apples kind of fall onto the tree. They make a noise as they fall. And then here, I actually have a touch laptop, so I can drag this with my finger over here and put the apple in the basket. And then, the kid would be counting 1, 2. And so I go and I put all of the apples sort of one at a time into the basket. And then once I have the last apple in the basket, the basket flies off the screen and I'm congratulated, right? And I could play again. And, the apples sort of come back into a new random location. And, I could imagine leaving the app, sort of coming back to it. When I come back, potentially, actually, I'm trying to remember exactly when it happens, but, oh yeah, there we go. When I come back to the app, you see the apples are already there, right? And so the apples wiggle on the screen. And so there's different states you could come back to. So, all right, well, how do I want to code this? It seems like this is pretty simple. There's just apples I want to drag, but there's actually a reasonable number of states that are going on here. I want to do those animations in the beginning. I want to do the wobble if I'm kind of resuming. I want to handle the drags correctly and all of that. So if we take a look at the code that the user had written for this, it ended up looking a lot like this, right? And so you don't have to understand what this code does because the user didn't, and we barely did either when we were looking at it. But what it really does, you can kind of sense what they were trying to do, saying, all right, well, I'm going to keep my control flow linear. I'm not going to put it as macaroni code, right, in a bunch of different little methods. I'm going to take charge and put all of this into one big method. But you see how it quickly gets out of hand. I say, all right, well, I press with a pointer with my finger and say, all right, well, now I'm going to add a handler to say, OK, when you press with the pointer, make sure that if the apple is pressed, then go through and do this stuff and see if there's more apples. Then I'm going to set this animation to say when we do this, OK, now that we're doing this, when the button OK is clicked, do this, which now goes back to here. But then if you wanted to go back to the beginning, how do you reference yourself? And you want to make it linear, but then you feel like you're kind of contorting yourself to do so because you have to deal with all of these nested lambdas, and it quickly becomes a pain. So, all right, that kind of seems like one of these places, nested lambdas. Maybe I can use await for that. But you notice a lot of the things here, like pointer released, button OK, click. Some of these are actually also about storyboards, XAML storyboards completing. When the animation is done, then I want to do something. Or when a sound playing is done, I want to do something. So you want to use await to represent these linear control flows, but it's hard to hook into those events in that way and bridge that gap. So initially the thought is, all right, well, maybe await's going to be weird. What if we just kind of make it a state machine? What if we do embrace it being a state machine, having a complex stateful UI? Let's kind of map out what we want to do here, and maybe we can just kind of make each one of these states a method, use some polymorphism. So, all right, well, what do we draw? Okay, you go into the intro, and you have a few things that can happen there. Maybe you care when the animation is done. You also kind of care when the sound is done. Well, okay, I don't want to move on until both of those are done, but maybe I'll deal with that. All right, well, now the animation and the sound are done, so I go on, I do some stuff. I'm kind of in this stable state, but okay. Now, what if they press, but they're dragging, and all right, well, they could be dragging different apples, and so I have to track that, and then there's apples in the basket, and okay, well, now if I want to add a feature, oh, crap, I'm resuming, aren't I? All right, well, I have to handle that, and quickly the whole thing goes off the rails, and you see all of these boxes that are here on the screen. Those boxes that are kind of scattered around the diagram, that's all of the actual meat of the app, right? That's the code that's actually doing something, that's showing the apples shaking, making animations, making sounds. That's the code we want to write. That's actually what we're here to do. But it ends up scattered all about our diagram, right? If we actually implemented this directly and kind of made classes or methods for each one of these nodes, we would be spending the bulk of our code on boilerplate about when things happen, rather than sitting there writing the actual the actual meat of what we want to do with our app. And so this kind of quickly becomes hard to maintain also. So the core problem here is events, right? Events are with us. They're a core part of UI frameworks, and for many cases, that is the simplest way you're going to want to do things. So events are not going away sort of in lieu of async or anything like that. So what can we do then? Well, think of an alternate way to imagine sort of a state diagram or a flow diagram for what happens within our app. Right? Instead of thinking of it as kind of, well, I'm in this state and then I'm in that state, just think of it as I have one kind of stable state I'm in, and I have certain things that happen on certain events. So when we start, I want to make apples and I want to show the animation. When we're resuming, I want to restore the apples and play wobble animations. When I'm pressing, I want to drag. Then I want to animate. Then I want to animate this. And I want to maybe have some if statements in there. But I can think of each one of these as just a linear flow. There's only a handful of ways the user actually interacts with the app. And then you're kicking off this kind of chained flow. So we do want to think of it in this linear way, kind of the way the user was trying to do it originally. That is actually a fine way to do it, but we just want a way to directly encode that. We don't want all this boilerplate that makes it so hard to go back and see what we were doing in the first place. And so, the core issue is that callback-based programming, the kind of programming we were trying to do in that original code snippet, when you're doing it with events, it's hard, right? If you have these event handlers, they're all independent, it's fine. You leave them as events, it's great. I click this, I do this one isolated thing. I drag this, I do an isolated thing. But if they start to feel like a state machine because they're all interrelated, I'm waiting for two of these things to happen, and I'm going to join up, I'm going to do some other stuff, await can often be easier, right? And the way you kind of bridge that gap between the event world and the task-based await world is with this type called task completion source. And we're going to see how that works. So just before we even go into task completion source, let's look at the code we wish we could write originally, right? This is sort of us encoding in VB code that flow that we had, right? That flow that we described, sort of linearly on paper there, saying, all right, well, I'm coming in, I'm going to await dragging, we're going to go through, then I'm going to kind of play this storyboard of the apples animating, I'm going to play a sound also, right? And then I'm saying task.whenAll. So I'm just kicking off the animation, kicking off the sound, and I'm saying whenAll to kind of join. So I do both of those. But that's simple. I just have one line of code to say resume when both of those are done. It's not some weird state tracking where if this is done, go here and then call this method. I just express it naturally. And then, once there's no more apples left, I show the victory screen, and I say, all right, well, play again, show the play again button, and when it's clicked, call back into onStart, right? So I'm able here, by being able to await button clicks and being able to await the victory screen sort of clearing off, I'm able to say, all right, here's a complex flow of how the user goes through different screens in my app, and then when they get back, I start again, right? So I can model that flow, even though it involves all different UI elements with one linear method that represents the way I kind of think of a user's walking through my app. So how do I actually implement these kind of play async, drag async methods? Well, if I look here, what's the core thing behind play async? Why is that tricky to begin with? Well, it's because I care about storyboards. This is about playing a storyboard. And a storyboard does have, in essence, an asynchronous API, but it's event-based. Because I set up the storyboard. You see I'm subscribing a completed handler to the storyboard, and then I'm calling begin. And by calling begin, I now kick off the storyboard. Let's say it's a 2-second animation. When the animation finishes, it's going to call my completed handler, and that's going to keep going, right? And so what I can do here with this task completion source type is kind of make sort of a virtual async method, right? I'm making a task that doesn't have like a thread behind it or even an async method behind it. It's a task that's just kind of a shell that I can say arbitrarily, hey, this task, you're now completed. Or this task, you've now had an exception, right? And I can return this task to my caller, and I keep track of this task. And by waiting for completion, and then saying, hey, once I'm completed, the task I returned is completed, I'm able to provide this kind of async illusion to my caller. I get to wrap around the complexities of how storyboards work and encode it in this one place in my code. And then anywhere else that I care about storyboards, I can just pretend storyboards have a play async method. And so let's actually track through here. You can do the same thing in C#. We'll track through and see how this works. So I come through here. Code enters my play async method, right? We get down. We sign up our completed handler that we defined above. And then we call begin. And so now we get down here to the await. And just like every time you get to an await, we return back. And our execution is done. We've gotten off the UI thread. Now the animation is going. It's some wobbling thing. It's going to happen for 2 seconds. It comes back. And when it comes back, I now go in again and say, all right, well, it's completed. The storyboard completed event is going to trigger. It's going to call my Lambda that I passed in for the completed event. And the one thing we do in there is we say task completion source, set result. And we don't even have a return value, so we just send null. So we tell task completion source to set the result. And what that does is it says, all right, well, because our storyboard is done, I'm setting the task that we returned before to be completed. So anybody who was awaiting play async originally now has their code resume. So somebody was able to use this to kick off something, whatever my storyboard play did here, and then track when it completed with that same async await mechanism that they were using for everything else in their code, right? Because this is now, when I say set result, this is now going to go back to this task. The wait's going to finish. It's going to complete out of this method. We're going to even unsubscribe the Lambda because we're good citizens there, and then we finish off. And so, it is a little tricky to follow at first, actually, so I'm going to show it again. For when clicked, right? So that was for a storyboard. That was us wrapping an existing on-completed event for a storyboard. In this case, we're actually just wrapping a direct click, right? This is a button click event. And so how do we wrap this? Well, it's pretty much the same thing. We come into our when clicked method. This is a method, again, is returning task. It's going to tell a user the moment that the button is next clicked. We come in and we say, all right, well, subscribe to button click. When the button is actually clicked, call into my Lambda. All right, we say that, we go to the await, and then we return. So we return, and it could now be 1 second, 10 seconds. The user goes off, gets a coffee, comes back. They finally click the button to say, OK, I want to go play another game. And when they click the button, the click event handler goes, the Lambda happens, and then control comes back into our completed event, right? And so now the task is set as done. And when the task is set as done, we come back here, we finish out our method, we unsubscribe, we reach the end of our when clicked method, and then everything now is returned, and we're actually already done, right? We've marked completion, and then the people who called us just get to continue on. So by actually having this flow where I can make task completion sources and have tasks and await them, right? You see here, I was taking that task that we made to track this. I was awaiting it internally. You could have other cases where I use the task completion source. I wrap something. I just give the task directly back to the guy who called me. I've made a task that's going to kind of be going on with my own flow in here, and when I say you're done for some reason, for whatever flow that I'm tracking, whatever API I'm kind of wrapping around. Whenever that's done, I mark it complete, and the guy directly has a completed task. So there's all different interesting things. You could search for examples online of people using task completion source to wrap various APIs. But the idea is that sort of with this one common pattern, you can apply this pattern to any event that you have and be able to know when that event is done. And be able to do that in an async way, right? Without having to think, oh, I'm going to subscribe a handler, and I'm going to have nested lambdas, and I'm going to get crazy. You can write this code once. Maybe sort of your senior devs in your org can write this code for the events that you care about, and then you have a very simple API that anyone can use to know when that's actually done. So we have, again, some more info if you want to go look at the slides afterwards. We have some hidden slides here around drag async, because that's kind of a two-parter, right? You start a drag, and then you end a drag, and so there's interesting stuff there about how you can use task completion source to track those two related events. Dispatcher.run async, this is, again, like you're back. You want to put stuff. You want to have task returning lambdas. You want to remember we saw before, it was taking a void returning lambda. You can actually see the code here for how you would write that wrapper for dispatcher run async. And also, like we have that on resume handler. How do we deal with resuming if we're potentially already in the middle of some stuff? And there's some cool things you can see there. And so you go back to these principles. Like, you do want to use events. Events are not replaced by async or something. You don't want to go wrapping every single event you have in this way. That's not the point of this. But if you start to get code that feels like you have a lot of interrelated events and you're kind of tracking this complex state across all of the different events that you have, and it feels like your code is turning into this unmanageable mess, consider kind of planning out the linear flow you wish you could write, and then you may be able to actually just wrap your events in this way, and then kind of tame that complexity, tame the event complexity within your app. So the one other thing we have here, the one other main tip, is really around threads and what it means to actually have I/O-bound code or CPU-bound code. And one of the questions we got was somebody who was making some sort of real estate app, some sort of ASP.NET app about real estate. You can think of kind of like a Zillow-like app that's going to show different houses and such. And they were going off to databases, they're requesting data, and they're saying, well, it's taking me about kind of like 100 milliseconds to deserialize and work with the data that I have here per house. And so if I have 20 houses, it's taking me like 2 seconds to load my page. I know I want to do these things in parallel. Is it right for me to use like parallel.for here to kind of use the task parallel stuff, or do I use plink? What's the right way here? And we saw this question and it says, all right, well, that's great. It sounds like you did some profiling. That's the first step you always want to do when you have a performance issue. It sounds like you did profiling and you realized that you found some chunk of CPU-bound work that's going on here. And if it's CPU-bound, then yeah, we have to find some way to kind of push it off to a background thread. And so it sounds like that's the right approach, but we'll see that it's easy to kind of fall into that trap of assuming you have CPU-bound work when it turns out your work really isn't. So this is the code, in essence, right? Sort of simplified version of the code that was there. And it's saying, all right, well, here's what we have now. Load houses. Well, I probably didn't write load houses sequentially, but helps us remember. Load houses sequentially is going to go through. You kind of have this list of houses, and we're going to deserialize them one at a time, right? He had this deserialize method. It's going to go off. This is the method he profiled and said it seems to take about 100 milliseconds. So I'm going to deserialize all the data for the house. I'm going to come in. I'm going to add it to a list. I'm going to go through and return it, right? And so this is the code here, and it's going to kind of go in order. And you can imagine that if each one takes 100 milliseconds, and I have a simple method like the one you saw that just loops through and does it one at a time, and it's going to take 500 milliseconds to do 5 of them. And so that makes sense, and it seems like we have some easy stuff we could do here to try to parallelize. So let's sort of take a first stab there. All right, well, load houses in parallel. So I could use some of the helper methods we have from the task parallel library. I could call parallel.for and say, all right, well, here's the body of what I want you to do for each house. There's going to be from first to last. Maybe there's 5 of them, right? And for each one, I want you to deserialize it. And parallel.for, it's great at taking CPU-bound work and figuring out how many cores you have and figuring out how many threads to make for that. And so what we want to be happening here, what we'd expect to happen is, let's say I have a 2-core machine that I'm running this on. Well, I expect that I have my different work items running on the different cores, right? And so maybe one goes to 1 and 2, and then after 100 milliseconds, all right, I'm going to schedule the 3rd and 4th one, and then the 5th one. And so maybe these 5 actually just take 300 milliseconds instead of 500 milliseconds. So that's an improvement. I'm doing the CPU-bound work kind of as fast as I can. But the question you always want to ask yourself when you're deciding, hey, should I use parallel.for? How do I actually make my code parallel and make it faster like that? Is, do you actually have CPU-bound work, or is your work really, under the covers, I/O-bound? Are you really waiting on either your disk to go do something and load some data, or are you waiting on a network machine, like a database server, some other web server, to get some data ready for you and send it back to you? Because if that's what you're waiting on, you don't really have blocked CPU cores. You just have CPU cores that are kind of twiddling their thumbs, waiting for something else to happen. And so it turned out that we sort of dug in deeper with this customer, and it turned out his deserialize method, well, one part of what it was doing was deserializing data, but it was really actually pulling in data. It was going to database servers, like 5 different servers, gathering data, kind of taking all this XML and munging it and pulling stuff out of it. And so it was doing some amount of that munging, but it wasn't enough to take 100 milliseconds. In computer time, 100 milliseconds is a really long time. You'd have to have a lot of data for deserializing to take 100 milliseconds. And so it turned out what it was, that was just the network latency, to go to the server, have it wait, queue up the request, send you the data back, was 100 milliseconds, which is reasonable. It's a reasonable latency. But it's not 100 milliseconds of work that your server should be doing. And so if you look here, you can picture these requests really as kind of a start and an end, right? There's like a little blip at the beginning, which probably takes a few microseconds to go kick off some request to a server. We're then waiting for the request to come back, maybe multiple requests. We get them back, and then we say, all right, we have these requests back. Let's process the data, deserialize it, and return it. And so the work you're doing on your server should be very minute. You're actually waiting for other servers to do this work for you. So really, there's this big gap in the middle of each work item. And so if we serialize it the way we did originally, if we make it sequential, it's going to take 500 milliseconds. But what happens when we use parallel.4, right? We had our kind of ideal parallel.4. It would take 300 milliseconds because we thought we had that much actual work to do. But we really don't, right? So what it's going to do is it's going to kick off the start of work item 1, the start of work item 2, and then the thread pool is going to say, well, actually, most of my threads now are kind of just waiting on I/O. They're not actually doing anything. The CPU is at like 0% usage. So crap, we must not have enough threads. Let's add more threads. And so the thread pool is going to say, well, let's add a third thread. Uh-oh, it's not enough, right? And so let's add a fourth thread. And so it's going to start adding more and more threads to your app, desperately trying to keep your CPU busy because you're giving it all of these tasks that are just blocking waiting on I/O. Right? And then maybe one of them finishes by the time the other one happens. And so you could imagine the thread pool adding threads quickly, and ideally maybe it would finish in 200 milliseconds. But in reality, the thread pool is a global resource, right? It's global to your application. And you might have all different code paths that are adding threads to that. And the thread pool has to be conservative. It doesn't want to spin up a whole bunch of threads and then get rid of them. So it kind of watches, and maybe once a second it'll say it's time for another thread, and it'll kind of change slowly. It uses this kind of modified hill climbing algorithm to decide how many threads it wants to have for sort of maximum throughput. It sees how pegged the CPU is. And so if this is when you first started your app, you're not even going to get to the maximum number of threads that you could have right away. So your CPU might be doing nothing, but all of the threads could be blocked, and it'll be a while before you get another thread to go handle work item number 3 and work item number 4. So actually, in reality, this could take over a second to process, even though your CPU is doing nothing. So ideally, if we think what we really want logically is to kick off all of the requests. We want to get all 5 requests kicked off at the same time going to the server. And that's just still going to take a handful of microseconds to just do all of those kickoffs. Then, we wait some amount of time, and the requests come back to us, right? And they could come back out of order, right? So N2 and 1, whichever ones come back first, we don't care. They're all going to come back in approximately 100 milliseconds, but they're coming back in parallel. So now the total time is going to be 100 milliseconds. And this is what we expect. When you parallelize I/O-bound operations, you should be able to sort of almost completely parallelize them, right? If you have 100 of them and they each take 100 milliseconds, you should be able to get all of them done in 100 milliseconds as long as your networking stack or your disk can actually handle that I/O that fast. And so you really want to keep track of this difference between, within your methods, do you have CPU-bound asynchrony or do you have I/O-bound asynchrony, right? CPU-bound work is going to be you doing a bunch of data crunching, right? Things like doing link over objects, right? Not link over SQL, right? But link over objects. Doing big iterations, inner loops that are going to be crunching on a whole lot of stuff. And if you have actual CPU-bound work, go ahead. Use parallel for each. Use task.run to just go dump the work onto a background thread, and you can even go manage it over there. So those are great when you have real CPU-bound work, kind of the focus of the task parallel library originally in .NET 4.0. And the thread pool is going to gradually feel out over time how many threads it needs to make the best progress, right? But it does that slowly. And if you have CPU-bound work, right, you saw before, and we did the original parallel.4, said you have 2 cores, well, you get 2 threads. And that's basically what it does, right? There's no point having more and more and more and more threads if you're actually just crunching data. You don't want to be doing needless switching, right? Adding more threads and dumping threads into the system doesn't help you increase scalability. If your server is already overloaded, you're not going to get any more throughput by having 10 times as many threads, right? You want to basically have as many threads as you have cores. But that's assuming you have all CPU-bound work, right? If you have I/O-bound work, and we have work in quotes here, right? Because it's not really work that your computer is doing. It's just logical work that you're sort of deferring or delegating to other people and having done on your behalf by other servers that are around your org, right? If you're going to do that, then use a wait. You don't want to use background threads when you're waiting on I/O-bound work. For CPU-bound work, you want to go use those methods. And this is a key point, if you're defining libraries or you're defining a helper method that could be used kind of in both cases, you don't want to do task.run. You don't want to be putting things off into background threads yourself. You want callers to decide how to do that. Because there's all different balances your caller might want to make. If they want to optimize for latency, that's different than optimizing for scalability, right? They might want to make a bunch of threads to do CPU-bound work if it's going to be little blips, right? If it's going to be blips and I want to do 10 of it once, and right, maybe I want to do that. And I want to get it all done super fast, right? But that's going to come at the cost of scalability, right? It doesn't increase scalability, it increases speed. I get a request and I need to do 10 things. If I do them all at once, it might take 100 milliseconds across all my mega cores on my server machine. right? But that's taking up all of those cores, right? Those cores are cores that could have been handling other requests from other users. So I'm just handling each request much faster, but other requests are actually going to be delayed before they can even be processed because I'm taking up all the cores to process this one. So you're trading latency against scalability, potentially bottlenecking your CPU and the number of threads that it needs. And that's a trade-off you want the app developer to be able to make. You don't want to sort of commit them to some strategy by you making a bunch of threads in your library. Let them make those calls themselves. So, all right, well, here's the API that we really wanted to write. Imagine you have load from database async. This is something that's going to take all that deserialized stuff. Internally, we're going to dig through. You don't get it for free, right? Task.run is something that could wrap a synchronous method. The solution, when you have IO-bound stuff, you got to dig into the method that you wrote and actually figure out where the network IO is, dig all the way to it, and make that asynchronous, and kind of bubble that asynchrony all the way back out. So you're going to have to go and change the way that these things are loaded. But assuming you do that, and you can implement a load from database async method, some helper method that goes and does all those network requests, actually asynchronously this time. Now up here, I can just gather those tasks up, right? Let's say I have 20 of these houses. I go from the first one to the last one. I add them to this list of tasks. I'm going to have 20 of them in that list. I then say task.whenAll, and I pass the whole list in. And then I only return when that's actually complete, when all of the tasks are complete, and I can return all of the values back to my caller. So one other place, though, so we were talking there about IO-bound work. You know, a lot of times you will have actual CPU-bound work, right? And for example, this is a case, it's a financial case. You think of like option pricing, right? And the way that financial analysts will go and quants will go and calculate stuff for option pricing is they'll do a bunch of simulations, right? So you could imagine here, I want to do 1 million different simulations of the stock market for a given stock and see what happens, assume it goes up and down with different variabilities, and then track what a given option would do over time, what the kind of expected value is. And so we know exactly how much we want to pay for that option. Well, you could imagine this kind of loop here where I'm going to say do it 1 million times, and if I wanted to do this on the UI thread, right, this would block my UI thread. Maybe this takes 10 seconds to calculate. That's going to block my UI thread if I do it directly here. So I want to stick it off on a background thread. You know, just to say, like, the code we have here, this was an example we wrote as we were kind of testing async, but you know, we kind of went to some of the people in MSR who track some of this stuff, who actually know about options pricing and how to calculate some of this stuff. They made a library that we could use to try this out in F#, right? And F# is really kind of this great way that you can go and do this kind of math-based programming. And so you let the people who really understand that stuff go do that, and then you think, okay, now I want to write my UI, I want to write my server app, and I'm going to do that kind of stuff on top of it in C# or VB. And so we have this library, let's say, that actually does that option pricing. So I call into it, that's the one that's there, quant.simulate stock price. And I'm going to do await task.run. Right? Task.run is that way that I have to take some work and dump it off back into the thread pool. And I'm able to await task.run to flow back into my UI code, right? And this is where I can get that easy ability to jump back and forth between the UI and my background thread without actually feeling like I'm kind of bouncing between all these different worlds or getting deeper and deeper into nested lambdas, right? I'm using my UI code. I get to a blip here where I want to do a bunch of background code. I do it. And you see below I'm returning from my lambda there. I'm returning the value I want. And that value is going to pop back out to expected payout, and then I get to continue on. And so, yeah, so basically here I have that ability to do background work. I'm not blocking my UI thread. And this really is CPU work. And so, you know, I'm able to do that. And you could imagine using parallel.4 here if you had multiple cores. But just to keep the core idea simple about how to use task.run, that's what I'm showing. And one other interesting thing is you think, OK, well, I want to go to the background thread to do the work, but maybe I want to start poking into the UI again to show progress. Progress is a common thing that you care about when you're doing CPU-bound work. You want to go update the UI. And then you could feel like you're getting into this bouncing. Well, start from the UI thread, do the work on the background thread, then kind of come back to the UI thread to show progress. That could get kind of hairy after a while. And so one of the ways we actually give you to support that is this progress type. And progress type actually kind of captures your UI context for you in a way that makes it easy to schedule that work back to the UI thread. And so you make this progress object here in your click event when you're still on the UI thread. And you give it a lambda saying, hey, every time you get sort of an integer progress reported, go set some progress bar's value to be that number, right? And you say, all right, that's what I want to do whenever I get a progress update. And then later, inside your lambda, you're able to say progress.report. And that's actually going to go. It's going to update anybody who signed up there as a progress handler, which we did. And we're going to actually have that lambda expression go update the UI for us. And we don't have to think about marshalling back to the UI because the progress object remembers the UI thread that it was on when it was created, and it stored that. so that it would be able to actually do this kind of transfer. So just like with the other sections, we have more that you can learn if you go in and you look at the disabled slides, the hidden slides here. We have some stuff and some of the new features in WPF 4.5 that actually let you update these collections from background threads, which is pretty cool. Key patterns, when you have code that kind of looks like it's doing something asynchronous, but it's not really, and those are some more gotchas, basically, that you want to be able to go through and take a look. And also, when you're waiting on the UI thread, it's usually pretty fast, but there are still some kind of costs that you can run into around CPU-bound work, even when using task.run. So for a few more of those kind of, how do I schedule work gotchas, you want to go take a look at that. It's more than we can kind of pack in all today. And so yeah, again, just those core principles. Definitely figure out, am I doing IO-bound work? Am I doing CPU-bound work? Those are two very different things, and you really need to know which is which when you're trying to figure out, hey, do I actually have scalability that I think I'm getting, or that I think I deserve here, right? And one of the ways that you get servers that are getting sort of 10x or 100x scalability than the servers we've seen before is by heavily embracing asynchronous I/O, especially when the server is going to caching servers or database servers. They're doing a lot of the heavy crunching. If your front-end server is a bottleneck, you may want to take some places where you are blocking on these kind of things that are really actually I/O work and find a way to make them kind of deeply asynchronous all the way down, in which case you can usually turn something that took like the whole process and block the thread for that time down to microseconds and scale way more than you could before. And yeah, the one thing to pay attention to, what thread am I on, right? That's the key around asynchrony. The key around await. Await always puts you back in the threading context where you were. I'm on the UI thread, I await, I end up back on the UI thread. I'm in the thread pool, and I await, I end up back in the thread pool. Remember that async, when you make an async method, it's not about just getting a thread or having a thread created for you. It's about knowing what thread you're on and putting your work logically back in the same threading context where you were. So just kind of keep that idea of threading in mind and where am I when I'm doing this kind of asynchronous work. So one of the ways I wanted to end this was just with some kind of common issues that people run into, kind of like a quiz in a way. Like we're going to have some issues, some sort of small snippets of code that we've seen in these user examples, and you guys can try to figure out what is it that's actually wrong, and what are the code smells that you should be watching out for in these cases. And so one of them here, like this is that one maybe we just talked about, right, where I have some sort of work, maybe there's like an action delegate, right? An action delegate's capturing some sort of CPU work, and I have a schedule async method, and someone says, I want to do this work on a background thread, so I'm going to make schedule async, and I put the async modifier on it, right? And it returns a task. I'm doing that correctly, right? And I'm going to pass this work there and calling it. But it's not running asynchronously. I called this from my UI thread, and the work takes 10 seconds, and my UI thread still blocks. But I used an async method, right? Why is my UI thread still blocking? So who knows why the UI thread is blocking here? Yep. It's because this actually really isn't becoming async, right? Even though you put the async modifier on the method, that doesn't actually put things off into a background thread. No line here has actually done anything to schedule work into a background thread. And that's that key thing to know. Async by itself and putting async on a method does not actually fork your code. It doesn't create a thread. It doesn't do anything. You have to decide to do that yourself. It's up to you to manage your threading. Await actually is very good about doing the opposite. Remember, it puts you back into that same threading context where you started. And so when you do this, this is just going to run synchronously on the UI thread. If you want this to run in the background, then what you want to do is you can avoid that whole helper method that was written. Just say task.run. That's the key. That's the API method that will take your code and shove it off and have it run as a work item in the thread pool. And so if you're expecting stuff to go in the background, make sure you see task.run somewhere in your code. The other thing is if you have a method like schedule async, don't accept arbitrary delegates unless you sort of have some way to know or you have some contract with your caller that they're going to be super fast or that they themselves are going to be async delegates. If you're running arbitrary code that you've accepted on an arbitrary thread, it might be the UI thread, and that could be very bad. So think twice before exposing a library method to your callers that might do something like this. So another problem you can have is something that completes too quickly. So let's say you have some method here, and you're going along, and it says, all right, well, task.delay 1,000, and I need to wait 1 second before I continue. But you run the app, and maybe the whole method completes in like 100 milliseconds, right? Like, why did this method not actually wait 1 second? Anybody know? Forgot to wait. You didn't actually await task.delay. You called task.delay, which created a delay task that's going to complete in 1 second. But you yourself have to say that you care about waiting for that task to complete. Just creating the task doesn't actually cause a delay, right? So what you want to do if you have an awaitable method, or if you have a awaitable object that's returned from a method, you want to make sure you go and await that. And the compiler will actually give you warnings in most cases when it detects that there's something that you should be awaiting that you're not awaiting, just because it's kind of easy to forget if you do a method call. This one's a bit trickier. So here I'm saying parallel.for, and I'm going from 0 to 10, and I make a lambda, and I'm doing a delay there. And I do make it an async lambda, right? So my lambda is asynchronous, and it's able to do the await. Now, again, I'm doing these 10 things, but this whole parallel.for just kind of completes instantly. So why here did my parallel.for complete right away? Because, well, I put the await. I do want it to delay, right? And I put the await in there, but it's not even, it seems to still. Well, that's the thing. So it is correct that it's going to return immediately, but it's going to return immediately because parallel.for, the delegate that it accepts, doesn't accept an async delegate, right? It accepts this action delegate, right? This is one of those kind of warning signs that you want to watch out for. When you're passing async lambdas around, expecting the method that you give it to be able to track when you're actually complete, rather than when you hit your first await, you better make sure that the syntax actually takes a func of task, right? It takes a task returning lambda. In this case, the syntax for body here is accepting an action of int. It just takes an int parameter and returns nothing. So this is actually going to turn into an async void lambda, right? So this is one of those cases that you want to watch out for. When you're calling with async lambdas, make sure they don't turn into async void lambdas. So the compiler's not going to warn you about that because it assumes that there could be an API that you want to call, that maybe there is some API where you're passing this and you want to schedule the work, and it could be that parallel.for is just about launching work. Maybe parallel.for doesn't intend to wait for the work to complete. It just intends to launch a bunch of things in some sort of way, and so you do care. It is okay there maybe to pass an async void lambda. So unfortunately, the compiler can't be sure. That's one of those things where you could imagine code analysis rules that kind of say, well, maybe you have a case for this, but in general, it's something you don't want to do. The compiler, unfortunately, has to be pretty conservative about the things that it warns you on. So yeah, this is one of those cases where you have an async void lambda. Again, use very extreme caution when you see an async lambda if you're not sure that the method on the other side is actually ready to take an async task returning lambda. And so here's one, and this is one that's specific to this task factory start new if you've done any of the .NET TPL, any of the task parallel library coding. Right? Like you maybe use Task Factory Start New today to kick off a bunch of tasks sort of in a tree. You're going to go kick them off and track when they complete. Well, you can pass async tasks now to those things. But what's actually happening here? When I'm saying await task.delay, this one still kind of completes too quickly. Like what's going on? Like, well, I'm not getting the task back that I expect. What it turns out is you're actually getting back here a task of task. You're not getting back the task that you expected from that operation. You're getting back a task of task. And it's because Task Factory Start New is really like you can pass an async lambda to it. But what it's really, and it is a func, right? And it is even going to turn into func of task. But it was really expecting a synchronous method. This is a method that was kind of trying to wrap a lambda and return you back a task that would sort of synchronous, or back and off in a background thread, give you a task that tracks that work. But it doesn't know about asynchronous lambdas specifically. And so it thinks, oh, I'm going to give you a method that runs the synchronous part up to the await and then gives you back the task that's returned by this method, right? It doesn't know about it. And so you get back this task of task immediately. If you were to await that and then await the task it comes back with, then you could but it's just kind of a mess. So basically, don't use task.factory.startNew unless you really need one of the advanced cases that it enables. One of the reasons that we created task.run in .NET 4.5 was specifically so it could understand async lambdas, right? That we could have something where you pass it the async lambda directly, and you're going to come out and have it know when it actually completes, rather than kind of returning immediately. If you do have to use start new for some reason, that actually is what you want, make sure you're actually unwrapping the task before you await it. We have an unwrap method on sort of task of task, lets you get to that kind of inner task, and then you could await that and get the behavior that you expect. So there's one other case here. Well, let's say I have, in my event handler, I have something where I had a foo async method that I want to call, and that is an async task returning method. And let's say I know, well, it's okay if my UI hangs here, nothing's animating, or maybe my delay was even shorter, like 100 milliseconds. I don't care about using async here. I'm just going to wait, right? So I decide to wait. I expect it'll block for 1 second here, right? Not the best idea, but maybe I hope it'll at least resume after 1 second. But I write this code. and it turns out my async or my UI hangs forever. So why did the UI hang forever in this particular case? Anybody know? It turns out the UI hangs forever here because we have a deadlock. And so what happens here is you're calling foo async. It's going into foo async and scheduling this delay. And remember what await does. Await says, do this operation, and when you're done, schedule the continuation explicitly back into my current thread, right? So if I'm on the UI thread, after the delay, schedule the callback as another message into the UI message pump. Well, that's fine, except that when we called foo async above and we were waiting for the second, we blocked the UI thread until foo async was complete. So we told the UI thread to block until foo async is done, but foo async completing is going to rely on the task being done. And so we're in this position where each thing is waiting on the other thing, and we've hit a deadlock. So besides the responsiveness issues of actually having that 1,000 milliseconds be taken up, right, by the foo async call and having the UI thread block, you actually can also cause deadlocks if you're synchronously waiting on things. So really, if you're writing event handlers, don't take kind of the cheap way out. Do your await, right? Make your event handler async, await your async methods. You can avoid not just performance issues, but you can also avoid deadlocks if the API was authored in less than the optimal way. Now, let's say now you're on the flip side. Let's say you are the library author, and you know you want people to await your method like this outside, but you know that some people might not. Some people might call .wait, .result, some of these synchronous methods on your task. Well, what happens if somebody calls a synchronous method on the task? How do we prevent the deadlock? Well, as a library author, you can code defensively against this. And one of these things you can do is you can add something called configure await. And what configure await does, it takes this parameter that says whether you actually want to do that scheduling back. So remember we said that await, by default, when you await something, it's going to say, oh, you were on the UI thread? I'm going to explicitly put you back onto the UI thread. But typically, when you're writing library code or when you're writing helper code, you don't actually care that after every one of your awaits that you're kind of put back explicitly onto the UI thread, because you don't know that necessarily you were called from the UI thread. You might be called from a background thread or anywhere. You're probably not doing UI-specific logic. So you could continue on any thread. If you're going to come back, you could be on a background thread. You could be on an I/O completion port thread. You don't care, right? As a library author, you typically don't care. As an app author, you care very much, right? But as a library author, you don't care. The default that we have here optimizes for app authors. But as a library author, you can add configure await false. So that it helps improve your performance a little bit because you avoid some needless scheduling, right? But it also prevents the deadlock. This prevents the deadlock because when we get to the async task delay, remember the deadlock was caused because that delay finished, we came back, we tried to schedule something in the message pump, but the message pump was blocked, right? But if we say configure await false, it won't try to schedule in the message pump. It's just going to synchronously run the rest of that code, the rest of this method, on whatever thread the task delay happens to finish on, right? And the task delay finishes, we go like this, and we say, all right, mark it complete, and now the UI thread is unblocked. So by using configure await in your libraries, you help improve performance a bit, but you also help prevent deadlocks. If people who are on the UI thread are kind of doing the wrong thing there, not the best thing, and they're blocking synchronously on your async API. So definitely consider doing that. One last trick around task completion source. So we saw how you could wrap existing methods that you had with a task completion source to kind of expose an async view over them, async view over events or so on. And so let's say you did something like that here with a task completion source, and you find that typically it's working, right? It works and it completes. You can await this kind of outer thing that you defined, and it's great. But sometimes it's not working. Like if there's an error with the code, it seems like the await never actually finishes. So what's the issue here? Well, it turns out the issue is that we've implemented that delegate optimizing for the success case. But if there's an exception inside foo, the exception is just going to get thrown, and it's going to get eaten by task.run, which is going to blow up, right? And then none of this stuff, this task, is never actually going to be marked complete. We never get to that set result line. And so whoever was kind of awaiting this task that we gave back at the outer level, they never get any completion signal. They're just sitting there waiting forever. So what you want to do is you want to make sure that you're always completing the operation that you're using with task completion source. Make sure that you've covered every branch and every case so that you will always have completion, whether it's successful completion or it's faulted completion. And so the way you do that here is you put a try-catch around the block that you care about, and then inside the catch you say, all right, well, if we had a problem, let's set the result of our task not to having a result, but to having an exception. You call set exception. And that says, all right, well, whoever awaited us, let's have them blow up there at the await and have the exception thrown, which is better because then they can catch the exception, they can deal with it at their level, rather than having it kind of surface somewhere else randomly inside the app. So again, to kind of review all of these things we talked about, async void, again, if you just want to have one takeaway, async void is for top-level event handlers. If you're starting off with async and you're finding you have issues where things kind of seem to work like 90% of the time, but they work differently, or they work well when you're testing on your super fast network, but they don't work well on a phone, on a cellular network, or somewhere else, it's probably something around you making assumptions and you using async void somewhere deeper in your code. You can use task completion source to wrap events, to sort of bring events into the async world. You can do that when your events kind of interweave and connect to each other in complex ways, and you have a lot of state to manage. And you also can use the thread pool when you have CPU-bound code. It's great. You want to use task.run. You want to dump work into the thread pool. That's actually what you should be doing. But make sure when you do that you actually have CPU-bound work. Dig in and make sure that your work isn't IO-bound. If it is, you could be leaving a lot of performance and a lot of scalability on the table. All right. That's it. Thank you. So we have a few minutes left. If anybody has any questions that they want to ask, any sort of async questions, you can come up to the mic, or you can ask me up here. Up to you. Sure.
My team is doing web forms-based applications that use Windows Workflow Foundation.
Mm-hmm.
And the user interface is sort of dependent on some database entries that get created by the Windows Workflow Foundation.
Sure.
But we have had troubles with how do we, so an action will get kicked off, some database things will happen,
right.
Some task-based things, or process-based things will happen. But we have had a challenge with how do we make sure that the user interface in a web forms app gets updated when this stuff is done.
Right,
and
right,
we've had to do some loops, and that's really smelly. It just is not
yeah,
right.
no, and like especially, it's not even limited to web forms, right? Like it's generally something around, like if you have background processes on a server, like sort of the way people are kind of moving now on sites is to have your page kind of come down immediately, and you have the AJAX kind of requests that go in. And you know, part of that is even just for scalability, because one of the cool things you can do if you do that is you could have your entire page structure kind of cached even by a caching server, right? Because it never changes, and always just have all of your data flow in that way. The problem is, yeah, it does require you to kind of rip out a lot of your web logic and put a lot of these things in. If, you know, unfortunately, if you're kind of interacting, again, from a web server down to a client, at some level you're going to have some sort of AJAX-like library that's going to be doing that kind of call. On the server, then it's going to depend, like whatever library you're using. It's sort of unavoidable at that point. When you actually have those workflows going on the server, though, there are some libraries that are out there. You probably want to go talk to the ASP.NET team. But there's some libraries out there that could let you actually kind of manage this workflow on a server, as long as it's not going to be like a workflow that takes like days or something. At that point, you don't want it to kind of be active. But if you have a workflow that might take like a minute or so, you could have a server that's actually just processing that. And hey, I want to send some data off back to the client, and you have kind of like a line that's going to go do this await thing, and you have an AJAX listener that's kind of hooking up to receive that message over like an open WebSocket channel or something like that. And so you can do some of those kind of tricks that let you then model your server flow a lot more linearly. Because you're just thinking of it, I do this, I wait for a while, I wait on some background thing in a database, I get the data, I send kind of over a socket thing, over a push to the client, right, and I keep going. So there's some of those tricks. The fancier the tricks and kind of the nicer your server code is going to be, potentially the more you have to kind of buy into with the stuff that you're doing on the client. The one thing I would do, I would actually head over to the booth area. There's some of the people here from the ASP.NET team. And actually, there was even a specific async talk that was around async and ASP.NET that was earlier, that was yesterday. And so you could check out the talk and go talk to them, and they'll have a lot more detail about ASP.NET. Thanks.
What is the async functionality that I can use with 4.0?
So the question is on what async functionality is there with 4.0. We have something called the async targeting pack. And so the async targeting pack will let you target .NET 4.0. It'll let you target Silverlight 5 and some of these platforms which haven't been updated yet to have async in them, the basic types that we need for async. You can do pretty much all the same things. The one catch there is that like we couldn't actually change the task type. Like a lot of these platforms, like .NET 4.0, for example, has the task type already. We did a lot of internal optimizations to task for async because there's a lot of new ways it was used. Back then it was used primarily for kind of data parallelism, kind of like a bunch of CPU-bound work you're going to push off. Now we want to optimize for I/O parallelism also. And so we did work to help speed that up. So you missed some of those optimizations. Otherwise, you should be able to pretty much do all the scenarios you could. The only other thing I could think of is if you're talking to other libraries, if you find libraries out there that people build against async, they're likely to have built it against .NET 4.5. And so they would have to have built that library having another version of it that would target like .NET 4.0 with the async targeting pack. And so you might have more limited ability to find those kind of libraries. But if you search for, I forget if it's still called the async targeting pack. I think there's a NuGet package that you can come up afterwards, we'll find it. But it's about sort of, I think it's called Microsoft.bcl.async. And you can find it on NuGet. And it's about letting you now go out and target those other platforms. All right, thank you.